Hello friends, welcome to the fifth segment of Thermodynamics of Polymeric System under the aegis of Polymer Process Engineering. Now in the previous lecture we covered about the statistical associating fluid theory that is called SAFT. Then we discussed about the SAFT application and then we discussed about the Vera equation of state. Now in this particular segment we are going to some more equation of state. First is the High-Danner equation of state. Then we will discuss about the Oishi-Prausimitz activity coefficient model. We will discuss about the Kumar equation of state, then van der Waals models, and again we will discuss with the Oishi methods for estimating the activity coefficient of solvent in polymeric solution. Now High-Danner equation, this High-Danner they modified the Vera equation of state by developing group contribution approach for the determination of molecular parameter. The basic equation of state from the Vera model, this remains the same, and that is the reduced pressure of ith component and the reduced temperature of ith component is equal to ln reduced volume of ith component, then again reduced volume minus 1 plus Z over 2 ln reduced volume plus Qi over Ri minus 1 over reduced volume minus theta I over reduced temperature. Now as in the Vera equation of state, the molecules are not assumed to randomly mix and the same non-random mixing expressions are used. Now in addition, as in the Vera model, the volume of the lattice site is fixed and assumed to be 9.75 into 10 to the power minus 3 meter cube per kilomole. The major difference between the High-Danner and the Vera model is that the molecular parameters, that is epsilon 1 and a reference volume, they are calculated from a group contribution in the High-Danner approach. The Vera formulation, let's provide a correlation method and the molecular parameter must be determined from experimental data. The High-Danner model, however, is capable of predicting polymer solvent equilibria given only the structure of polymer and solvent molecules. So the molecular interaction energy parameter epsilon ij is calculated from group interaction energy, that is EKKT and EMMT using the expression. Now we are going to give the expression. Epsilon ij T is equal to theta K I mm T to the power half. Now the surface area fraction of the group K in the component I, and theta Ik is calculated from the number of group of type K in component I and the surface area of group K. So theta I is equal to Vki Qk over Vm Qm. The molecular hardcore volume or reference volume V is calculated from the group reference volume Rk, and you can use this particular equation, that is Vi At plus summation K Vki into Rk. The molecular interaction energy and reference volume are function of temperature. Now the extremely effective UNIFAC model, that is a universal functional group activity model, this was improved by Oishi and Prausnitz in 1978 to incorporate a contribution for free volume differences between the polymer and solvent molecule. Now Starvanman combinatorial expression and residual term derived from the Guggenheim's the quasi-chemical theory, they are both used in the unifact model. Now, Oishi et al. They acknowledge that the free volume variation between the solvent and the polymer molecule are not taken into consideration by the unifact combinatorial contribution. Now, while this particular difference is usually not significant for small molecule, it is important for polymer solvent system. Now, they therefore added a free volume contribution derived from the expression, that is the weight fraction activity coefficient of a solvent in a polymer. So, ln omega 1 is equal to ln A1 W1 is equal to ln omega 1 C plus ln omega 1 R plus n ln omega 1 Fv. The free volume contribution is given by ln omega 1 Fv 3C1 ln reduce volume 1 by 3 minus 1 is volume 1 by 3 minus 1 minus C1 reduce volume 1 over reduce volume m minus 1 into reduce volume 1 over 1 by 3 V1 1 by 3 minus 1. Now, here this C1 is an external degree of freedom parameter for the solvent. Now, this Oishi-Prausimitz model, the unifact free volume is currently the most accurate method available to predict the solvent activities in polymer. Now, this required the Oishi-Prausimitz model. They are densities of a pure solvent and a pure polymer at the temperature of the mixture and the structure of the solvent and polymer. The molecules that can be constructed from the groups available in the unifact model, this can be treated. Now, at present, in this activity coefficient model, the groups are available to construct alkanes, alkynes, aromatics, water alcohols, ketones, aldehydes, esters, ethers, amine, carboxylic acid, some chlorinated compound, brominated compound, and few other groups for specific molecules. Let us talk about the Kumar equation of state. The Kumar equation of state is modification of the Vera model, which we have discussed in the previous segment, and that was developed to simplify the calculation for multi-component mixture. Now, since Vera equation is based on the lattice model with the quasi-chemical approach for the non-randomness of the molecules in the mixture, the quasi-chemical expression must be solved. So, the Kumar modification to the Vera equation of state, this involves computing a Taylor series expansion. All of us are aware about the Taylor series. So, Taylor series expansion of the quasi-chemical expression around the point where the interaction energy are 0, and that is the case of complete randomness. Now, this operation produces an explicit result for the non-randomness factor, which can then be incorporated into the derivation of the equation of state and chemical potential expression. So, the resulting thermodynamics expressions are cumbersome, but rely only on easily programmed summation. So, the advantages of Kumar equation of state, they are purely computational, and the resulting expression, they are approximation of the Vera equation of state, and that will reduce the proper form of for random equation. So, the Kumar, they stated that the expression of Vera differ because of errors in their work. Now, thus the discrepancy between the Kumar equation of state and the Vera equation of state must occur in the approximation due to the Taylor series. Let us talk about the van der Waals models. Now, the generalized van der Waals model or van der Waals partition function is used to characterize each and every equation of a state. The statistical thermodynamic is the foundation of generalized van der Waals model, and it is challenging to talk about the model without using the statistical thermodynamic language and intricacies. Now, this generalized van der Waals model, this relies on the concept of the partition function, and the partition function relates the most probable distribution of energy states in a system of molecules to the macroscopic thermodynamic properties of the system. The energy modes, these can be divided into translational or rotational, vibrational, electronic and attractive models. The translational energy state depends directly upon the volume or a density of the fluid, that is more specifically on the free volume, and for small molecules the rotational, vibrational and electronic mode, that depends only on temperature. For large molecules, however, the rotational, vibrational modes also depend on the density. The attractive energy of the system depends upon the intermolecular forces between the molecules, which in turn depends on the density and temperature. The density is usually dependent on the molecule's positioning and average spacing distance. So, the generalized van der Waals theory, this makes use of the radial distribution function, and whereas the lattice model specifies the placement of the molecules or polymer segments in terms of places on the lattice. The likelihood of discovering the center of another molecule is expressed mathematically as a function of the distance from the center of the first molecule using the radial distribution function. Now, it is depending on the system's temperature and density. Now, thus we arrive the partition function Q, this one, which is a complex function of temperature, pressure and density. The key connection between the complex partition function and the equation of state is a relatively simple relation, and this is a very common relation, which is equal to P is equal to RT del ln Q over del V at constant temperature. Now, this Oishi method for estimating the activity coefficient of solvent in polymer solution. Now, this method is to be used to predict the activity coefficient of a low molecular weight component in a defined liquid mixture containing 1 or more solvent in a solution with 1 or more polymer. The molecules must first be divided into groups as defined by the method, and the model parameter for these groups or group area, sometimes referred as a group volume, and the group interaction parameter, these can be either obtained from specified tables. So, the procedure also requires the densities of the pure component, both solvent and polymer, and the molecular weight of all components, and the activity coefficient, because ultimately the activity coefficient is needed. So, the activity coefficient of the solvent in the solution is given by ln omega I is equal to ln omega I C plus ln omega I R plus ln omega I free volume, where this ln omega I, this is the activity coefficient of solvent I at temperature T, and this is the ln omega IC, the combinatorial contribution to the activity coefficient. This one is the residual contribution to the activity coefficient, and this one is the free volume contribution to the activity coefficient, and temperature T, which is in the kelvins. Now, the combinatorial contribution of the activity coefficient is usually given by this particular equation, ln omega I C is equal to ln phi I y plus 5 q I ln theta 1 phi I plus Li minus phi I mi and summation j wj Li over mj. Where Ij is equal to 1, 2, 3 m, that is number of components in the solution. Phi I is equal to the number, the molecular volume fraction of component I. Wj is the weight fraction of component I in the polymer solution. Qi is the surface area parameter of component I. Theta I, the molecular area fraction of component I. Li, a parameter for component I. Mi is the molecular weight of component I. Number average is recommended, and that is in the kilogram per kilomole. The molecular volume fraction for each component I is usually given by phi I is equal to Ri Wi over Mi summation j Rj Wj over Mj. So Ri is the volume parameter for component I. So Ri can be given as summation K I R K. Now here the Vik is the number of groups of type K in molecule I. Rk is the group volume parameter for a group K, and K is equal to 1 to n, that is the number of groups in the solution. So the molecular area fraction for each component I is given by theta I is equal to Qi Wi over Mi summation I Qj Wj over Mj. So the area parameter for each component I is determined by Qi summation K Vk I Qk, where Qk is the group area parameter for group K. The residual activity contribution to the activity coefficient for each component is given by ln summation K Ki ln Ki. Now this ln omega I r is equal to K Vk I ln Ki. This is the residual activity coefficient of group K in the defined solution at the given temperature T. And this is the residual activity coefficient of group K in a reference solution containing pure component I at the temperature T. So dear friends, in this particular segment, we discussed about the different model and equation of state pertaining to the polymeric system, especially dealing with the thermodynamic system. And for your convenience, we have enlisted several references which you can utilize as per your need. Thank you very much.